Okay, today in this video we are going to start the discussion on Noether's theorem, and we are going to derive this theorem, which is a very profound theorem. But before I do so, I want to talk about symmetries in not in quantum field theory context, but in the context of classical mechanics that you already are familiar with. So, you know that momentum is conserved. Okay, so this is something which we have learned in our school, that momentum and energy is conserved, and in your classical mechanics course you would have learned why these conservation laws hold. Okay, and you must have learned that it's the invariance under space translations that leads to momentum conservation, and invariance under time translations, meaning if you have symmetry under translations and under time translation and under space translations, then you have momentum and energy conservation laws. Okay. So, for example, you know that if you have a free particle, I am just taking one example, and if the space is homogeneous, okay, all these points are equivalent, then if this guy has some momentum, I mean, you can assign it a momentum p which will not change with time, okay, because it's a consequence of space being homogeneous or having translation invariance. Okay. But suppose I want to spoil this symmetry. I don't want to have space invariance, translation invariance, then of course momentum would not be conserved, and that is also familiar to you. So, what you can do is you can put a massive object here, say earth or sun or whatever, and now different points in space are different. Okay. Now, this point is not same as this point anymore, okay, because here when the particle is at this point, it will experience a different strength of force compared to this one. Okay, so different points are now different, and you know that momentum would a particle which is falling on earth, for example, its momentum will keep changing with time. So, if you were to release something at rest, okay, then momentum is 0, but then it is going down, its momentum keeps increasing. So, momentum is not conserved because you have destroyed the homogeneity of space by introducing a massive particle here or massive object here, which is earth or whatever. Again, you can of course spoil this translation invariance in many other ways. But if you were to take both of these together as part of the system, the particle and the earth, then this entire thing together taken as a system is living in a space which is homogeneous. So, if you were to take the entire thing and translate to here, nothing changes, and that is why you have conservation of momentum, not individually for this particle and the earth, but both taken together. So, the momentum of the system would be conserved, right? And we have been talking about different theories. So, one theory which we have been looking at is that of Klein-Gordon theory, and we have seen that this is invariant under space-time translations. Let me write this. Okay. So, this is the situation that you had when you had a free particle here. Okay. It is equivalent to that, like this system has translation invariance. So, what would be the analog of this situation where the time translation is broken? So, let me spoil the translation invariance in this action. So, I will do something so that it gets spoiled. So, you can think of an action which is like this. You can construct many more which will destroy the symmetry. Let us keep this term unchanged, let us not spoil this one. Okay. If I have such a term, then the translational invariance is gone. So you can try to check whether action remains invariant when you take x going to x plus a, okay, and phi of x, phi tilde of x is phi of x plus a. Okay. So you'll see because of this term, it is going to be different. Okay. Clearly, this x square here, okay, is distinguishing different space-time points. Okay, because at x equal to 0, it's you have something else. At x is equal to some other value, it has something. You have your fields are multiplied with some other values. Okay, so different space-time points are now behaving differently, and you will not expect a momentum conservation here because of this broken symmetry. Okay, so here is an example of how you can destroy certain symmetries. In fact, you can destroy Lorentz transformations, Lorentz symmetry also. So right now you have x square, which is Lorentz invariant. Now imagine instead of this, if you had something else which does not respect Lorentz transformations at all, so x mu, or so this will not be scalar anymore, okay, or whatever. You can make it worse by putting just this. So that will spoil your Lorentz symmetry as well. Okay, so whatever symmetry you want to destroy, you can easily destroy by putting terms which do not respect the symmetry. Okay, so now what I want to do is talk about conservation laws in quantum field theory. Okay, and that work is due to Noether, and she found this profound theorem which goes by her name, Noether's theorem. And I was looking at some dates, and I found that this was a work which she did in 1915, and I think one paper in 1918. I'm not trying to be very accurate in the details, but this is the period in which this theorem was proved by her. Okay, and so let me write Noether's theorem. And it was around the same time when Albert Einstein was developing GR. So he wrote his papers on GR starting 1916. So this is the time when he gave GR. So you see, this is at the same time when this GR came about and Noether's theorem came about. And both Einstein and Noether have had profound impact on the way we do modern physics. Okay, that entire thought process of doing modern physics is heavily influenced by the works of Einstein and Noether. Okay, so all that we have been doing so far, that way of doing is heavily influenced by Einstein because it's all based on symmetry. And Noether gave us the conservation laws that come out of symmetry, and that's what we are going to talk about today. Okay, so here is the theorem. Okay, so we are going to be looking only at, this theorem concerns invariance of action which we have been writing as S under a global continuous symmetry. Okay, so global meaning the parameters which parameterize the transformations of the symmetry, they are constants, they do not depend on space-time points, and the symmetry is continuous. Okay, it's not a discrete symmetry. So this is what theorem concerns about, and because it's a continuous symmetry, I can go close to identity meaning no transformation at all, okay, and look at infinitesimal transformations. So, I will be looking at infinitesimal symmetry transformations. Okay, so let's assume that you have several fields in the problem, phi 1, phi 2 and so forth, let's say n of them, which I will collectively denote as phi a, okay, and these could be scalar fields or vector fields or spinor fields or other fields, okay, whatever they are. So, let's take a infinitesimal symmetry transformation such that under this transformation a field configuration phi a of x. So, you have, let me draw it in one dimension, okay. This is t comma x, so but I can only draw in 2. So, I have chosen this entire line to denote t comma x, and you are given some field configuration, okay, something. So, I do a transformation and it goes to phi tilde a of x, which is related to the original configuration by this. Okay. So, the field gets modified at each space time point and the modification is equal to epsilon psi a of x. Okay. So, if you have and of course, there will be order epsilon square terms if you are looking at, or you can in fact just say that I have transformed field by this much and this is the symmetry transformation. Okay. Now, because it is a symmetry transformation, the action should not change. So, whatever the value of action was, okay, S is a functional, right, it depends on the entire field configuration. It gives you a number when you specify the entire field configuration. Okay. So, S of phi a tilde, okay, is equal to S of okay, and because it is a symmetry transformation, I have assumed, then this has to be just this, okay, it cannot change, the value of the function cannot change under a symmetry transformation, or rather that is when you say it is a symmetry transformation, when action does not change. Okay, and we should keep in mind that the field that appears here, okay, I have not assumed anything about it. I have not assumed that it satisfies equations of motion. This is a general field configuration. There is no further assumption on it, okay, and because it is a symmetry transformation, this will remain the same. Okay, so no assumptions have been made about phi satisfying equations of motion. Okay, that is good. So, let us see here. Now, that is point number 1. We will we are going to use. I wish I could write. Okay, maybe I should write it on the next page again. So, under the transformation, I have S of phi a plus epsilon psi x. Okay, this psi a is made out of the fields phi and their derivatives. Okay, that is all. That's all that can happen. So, if you are changing a field, the new pieces which will appear will be either made up of phi's or their derivatives. There is nothing else, and epsilon is the small parameter of transformation. And this we said that this is same as S of phi because it is a symmetry. Okay. Now, let us do something else. Now, let me consider transformation which is not a symmetry. Okay, maybe let me write it this way. So consider a transformation where phi a goes to phi a prime. Okay, maybe I should show the x. And what is phi prime? Phi prime is related to phi in the following way. It's I'm sorry, I want to do again. Sorry. So here this is symmetry, and what was the transformation I looked at? It was this: phi a of x goes to phi a prime of x, sorry, phi a tilde of x, which is phi of x plus epsilon psi of x. So this was the symmetry. This was the symmetry transformation. Okay, and this is the consequence of it, that the action doesn't change. Now I want to look at not this transformation but a slightly different transformation where phi a goes to phi prime of x, which is phi of x plus epsilon of x psi of x. Okay, this psi and this psi are same. Here epsilon was a constant, it was a continuous parameter, but a constant continuous parameter. But here I have made epsilon a function of x. So this is still small, this is still an infinitesimal parameter, but that parameter depends on space-time points. Okay. Now we are saying that we are looking at global symmetries. So this is a symmetry transformation, but this is not. Okay. So this is not a symmetry transformation. Okay. Now let's ask what happens to the action when I do such a transformation. So if I start from phi x, okay, then there is some value of the action, and what happens when you do a small change like this. So what we want to know is what is this object, how it is related to S of phi a. You can put a or epsilon square pieces also. Okay. Okay, so because you have changed the field configuration, which is proportional to an infinitesimal parameter epsilon, the action should also change by an infinitesimal amount. Okay, so it will change by some term which will be order epsilon, and of course there will be higher order pieces also, order epsilon square, order epsilon cube, and so forth. Now I am interested in this object, how much it has changed. Okay. Now let's write down the most general expression of this term. So because S is a functional of the fields, this object also has to be a functional, right? That is of course obvious thing, that it has to be a functional. So and constructed out of the fields and its derivatives. So this piece will be something of this form and something constructed out of fields and derivatives, and of course this has to be an order epsilon term, so epsilon also should appear inside. Okay, and only one power of epsilon. You cannot have more powers of epsilon here. Okay, because the first term is order epsilon. If you are looking at some other term which was order epsilon square, that one will have epsilon square terms, but this one will have only linear epsilon dependence. Okay, so that's what we are able to say. But then we have constructed this transformation in a particular manner such that if I take epsilon to be constant, then this transformation collapses to that transformation, right? Because this epsilon becomes the constant epsilon and psi are same. I should not have missed a. Okay, meaning in the limit epsilon becoming a constant, this transformation should become a symmetry transformation. Okay. And this term should vanish, right? Because the moment you have symmetry transformation, you should get only S of phi. The value should not change. So it means that this further we can say that should be of the following form. It should be made out of the fields and derivatives and epsilon dependence should be such that it should reflect this fact. And I can ensure that by saying that epsilon can depend only as derivatives, because if you have a derivative, let me go slow, because if you have a derivative of epsilon, okay, then the moment you say epsilon is constant, all the derivatives will go to 0, right? Derivatives of a constant object is 0. Okay. So from this we conclude that as far as the epsilon dependence is concerned, it can be in this form. So derivatives of epsilon, what are those derivatives? You could have del mu of epsilon, or you could have 2 derivatives or n number of derivatives on epsilon. So you have d4x epsilon del mu epsilon of x times other objects which are made out of the fields and the derivatives, plus you could have del mu epsilon of x, and of course you can have other things multiplying made out of fields and derivatives and so forth. Okay. So this much we are able to say, but then you realize that this is the mu index is free here, and I should contract to make it a Lorentz scalar. So whatever quantity you put in here should have a vector index mu. So let me call it k1 mu. Okay, and k1 mu is the object which is made out of the fields and derivatives. Here you have 2 indices, mu and nu. So this object is a second rank tensor. To turn it into a scalar, because your action is a scalar, Lorentz scalar, I should have object with 2 indices, mu and nu, okay, which I can contract with this mu and nu to construct a scalar, and so forth. Okay, so what I have said is that this is equal to maybe here same thing, S of phi a plus integral d4x del mu epsilon x k1 mu plus del mu del nu epsilon x k2 mu nu and so forth. But all the terms are linear in epsilon. Let me see if I wanted to say anything more here. No. Okay, and then of course there will be order epsilon square terms. Okay, so this this fact that the action should take this form, okay, depends on the fact that we are looking at a transformation which collapses to a symmetry transformation when we make the parameter a constant. Okay. Now what I can do is I can take these derivatives and remove it from epsilon and put on the k, okay, so that the epsilon is freed, and that I can do by integration by parts. So I have to do integration by part once, and that will go there, and of course it picks up a minus sign. And similarly I can I can do integration by parts and shift the derivatives on k and so forth. Okay. So let me write it down. So my action becomes now which is just s of I plus epsilon x psi of x, and this I have shown that this is equal to s of phi a plus integral d4 x, and if I pull out the derivatives from epsilon and transfer to the other case, okay, I will have this form epsilon of x, okay, and then you will have del mu j mu, okay, and the j mu is constructed out of the k's and the k2's. So if I pull the derivative here, it becomes minus del mu k1 mu. If I do it twice, it becomes the two derivative get transformed on here, and that entire thing you can write it as like this, okay, and this is okay because you see all the both the indices are contracted, okay. So if you are not sure that it's obvious, please do it in do the one step in between and transfer the derivatives here and here, the two derivatives will transfer here, and then pull out a single derivative like the del mu here, and whatever remains is your j mu, okay. So what we have concluded is that under this transformation, the order epsilon term changes like this, or the order epsilon piece is this, okay. It has this specific form that epsilon is multiplied with del mu j mu. Okay, so this is all we can say based on symmetry, okay. So all that has gone into this argument is just this symmetry information, and then we have looked at an arbitrary transformation around the field configuration phi a. Now I cannot say anything more based on just symmetry, okay, but now what I will do is use equations of motion. Okay. Now I say that I am interested in those field configurations that satisfy the equations of motion, and ask what happens then. Can I say more? Okay. So if your field configuration phi a does satisfy equation of motion, okay, then you know that S is stationary at that point, right? S is stationary there. So if the field configuration satisfy equations of motion, you are here. So I am assuming this represents the value of S. Different points correspond to different field configuration, and for field configuration that satisfy equation of motion, you are here. And the moment you make slight changes to field configuration from this, you either reach here or reach there, okay. And what is special here? The special here is that if you change the field configuration by order epsilon terms, the action does not change by order epsilon, but it changes by order epsilon square, okay. That's what it means to be stationary. The first derivative is 0, okay. So if I use equations of motion, meaning if phi satisfies equations of motion, then this transformation which is written here, okay, under that transformation the action will become S of phi a plus this term cannot be there because of what I have said here, and only order epsilon square terms will be there, okay. So your change will be order epsilon square and not order epsilon. So if you use equations of motion, then you have Okay, and where you remember that J mu is constructed out of fields that satisfy fields and their derivatives, and of course now they have to satisfy the equations of motion. Okay, those fields which are entering into the J. Okay, then only this statement is true. But here we never said what epsilon really is. Okay, except for the fact that it should behave properly so that all the boundary terms that are generated when I am taking a partial doing integration by parts, those terms can be discarded. Okay, when you do integration by parts, you generate boundary terms, and I have said that assume that the epsilon behaves in such a way that those terms can be discarded. Okay, so if you take epsilon to be 0 at the boundaries, then you can discard the boundary terms. But other than that, I have not made any assumption about epsilon. So what does that imply? It says that because this result, this integral has to give you 0, no matter what epsilon is, this can work only if del mu J mu is identically 0, not otherwise. Okay. So this implies that del mu J mu is equal to 0, and this is a conservation law. This is saying that the current is conserved. Okay, and J mu, let me write specifically, constructed out of fields and the derivatives, and equation of motion should be satisfied. Okay, because if equations of motion are not satisfied, you are stuck at this point. Beyond that, you cannot say anything. This statement relies on the fact that your action is not changing to order epsilon. Okay, so that's the important thing which we have found. We have found that we have a conserved current. Okay, and let me now manipulate this a little bit to arrive at a conserved quantity. So you have del mu J mu equal to 0, and of course different field theories will have different J mu's, and different within a field theory different symmetries will have correspondingly different J mu's. Okay, so let's write this explicitly. This is just del 0 J 0 plus del I J I, and that is 0. Okay, this is just your partial derivative of time. I can write it this plus this is gradient del I, this thing is gradient. So you have divergence of J, okay, which is just saying that the time rate of change of this J naught at that is just the divergence of J. Okay, so right now this is a local equation. Okay, because at each space-time point this is true. Now what I will do is I will do the integral over all space and time. So I have del over del t integral d cube x J 0. So this I can take inside the derivative because this is integral over space and that's a derivative of time. So these two can be written like this. There is no problem. Okay, so they commute. So you have J naught, and that this is equal to minus divergence of J. Okay. Now here, once you have done the integral over all the space, okay, there is no reference to any space points, and this is no more a function of x. There is no x in here, and the partial derivative I can replace by total derivative. There is no distinction now between d over dt and del over del t. So I can write this as d cube x j 0. Okay. And on the right hand side, I assume that the current j, okay, there is no current flowing at infinity. So what I am saying is I am turning this, which is a volume integral, into a surface integral. So instead of d cube x divergence of j, I write it as a surface integral of j. Okay. And if I assume that there is, let's say the fields are vanishing at the boundary, which is at infinity, okay, then this will be 0. So if I take the fields to behave properly, I can write this right hand side to be 0. Okay. Let me call this object as q. Okay. So q is integral d cube x j 0. So this says that dq over dt is equal to 0, meaning q is a conserved quantity. As fields evolve in time, okay, no matter what they do, as long as they satisfy the equations of motion, dq over dt is going to be 0. Okay, and this is the conservation law. Okay, and q is called a conserved charge. And we have proved Noether's theorem that if you have a continuous symmetry, there will be a corresponding conservation law saying that dq over dt equal to 0. Okay. Okay, we'll stop this video here and we'll continue our discussion on Noether's theorem in the next video.